And again, this is not new to us. We've already done this before. We've already done quantifying equilibriums because we've done KEQs. It's the exact same thing. So for us to quantify the strength of an acid or a base, we're looking at that K value again. Now, instead of saying KEQ, we say Ka because it is the equilibrium constant for acids. Or it could be Kb, the equilibrium constant for bases, okay? Same idea. Anything greater than 1 is considered strong, okay? Anything product favored, we consider a strong acid. Now, for acids, you don't really get things close to 1. So once you are above the 1 number, they go into the hundreds and thousands very fast, okay? Your general equilibrium expression is as follows. Everything is in solution, and then a certain percentage splits apart into ions, and a certain percentage stays together. So we can represent that by the hydrogen ions produced, the conjugate base that gets produced from this splitting, and the original unionized acid as your reactant. Okay. One thing to note: if you have a polyprotic acid, each hydrogen in a polyprotic acid, okay, meaning diprotic or triprotic, has its own Ka value. Okay. We mentioned it a little bit before, but so like for example, we talked about sulfuric acid having 2 hydrogens in it. So that second hydrogen in sulfuric acid would have a different Ka than the first hydrogen. So for acid-base chemistry, you don't ever remove 2 hydrogens or 3 hydrogens at a time. It's 1 hydrogen at a time in terms of looking at it through that lens. Okay. So is there a Kb? Sure. Yeah. If there's a Ka, there's a Ka. There's a Kb also. So constant for bases. Same idea. The only difference is we need a little help from water to show this because we need to get hydroxide in our equilibrium, and not all bases have hydroxide in them to start. So if you take your base, including the water in that solution, you're going to get the conjugate acid now, which now it's gained a hydrogen with that base, and it's going to have that hydroxide. Okay. So again, we see our Kb value is your conjugate acid. You have your hydroxide, and you have the original base that would be non-ionized in there, all right? So we can look at the relative strength of these things by just referencing their Kas and Kbs. So here's a table for us to take a look at. This one happens to just be a Ka table, but we can look and say, oh yeah, sulfuric acid, large, Ka. Formic acid, okay? It has a Ka of 1.8 times 10 to the negative 4. So it's considered a weak acid, okay? It's less than 1. It's going to only partially ionize in solution, okay? Looking down here, oh, look, there's water as an acid. It's 1 times 10 to the negative 14th. Oh, look, there's that 14 again that we've talked about before, okay? Which would make sense because its conjugate, the hydronium ion, has a Ka of 1. So these two together, if you multiply them, would equal the Kw. Side note. Here we have, let's find sulfuric acid, H2SO4. Notice how that one is large. If we go down here and find the hydrogen sulfate ion, now this is the second ionization of our H2SO4, we see that it has a Ka of 1.2 times 10 to the negative 2. Still relatively strong, but not considered a strong acid at this point, okay? So in terms of what it has over here. Carbonic acid, H2CO3, we see that, pretty weak. And then if you go down here, the hydrogen carbonate ion, the second ionization of that is even weaker, okay? So the second and third ionizations of an acid, if they're diprotic or triprotic, are always weaker as you do that, all right? We're not going to do much calculating with this beyond the stuff that we've done before in terms of KEQs, but for us, it's more a reference that, hey, if you want to know the strength of an acid or a base, you can reference a Ka table and say, oh, here we go, hydrofluoric acid, its Ka is times 10 to the negative 4, so it's going to be weaker than this acid, so it'll produce less hydrogen ions in solution, all right? That's what we're kind of looking at as we do our stuff. Now, why do we care? Okay, so all this stuff about strength of acids, so why do we care? What does that do for us in terms of the chemistry? Well, there's some conceptual things that we can take a look at because we're not diving deep into the math here. First is, the stronger the acid, the stronger the electrolyte, okay? So you're going to get more electrolytic behavior out of that, okay? The stronger the acid, the lower the pH at the same concentration, or the higher for a base, okay? So what I mean by that is, if I put 1/10 of a mole of hydrochloric acid into solution, or if I put 1/10 of a mole of a different acid in solution, my pHs will not be the same. And I'm again going to bring that FET app down in to show you what I mean by that. So we can get rid of this and get to our a pH meter now. If I go back to acids and I bring my concentration down, let's put it at 0.1. That'll work. Okay. And if I go to someplace in here for a weak acid and I drop my pH in, okay, so I'm getting a pH of 2.69, all right? Now notice, I'm not going to change my concentration, but if I make this a weaker acid, my pH goes up, okay? Because a weaker acid is going to have less hydrogen ions in solution. Remember, pH is directly related to those hydrogen ions in solution, okay? If I switch this over to a strong acid and make it a strong acid, a concentration of 0.1 has a pH of 1. Okay. If I go to a concentration of 1, it has a pH of 0. Okay. A concentration of 0.01 or 10 times less concentrated has a pH of about 2. That should be exactly 2, actually, if it was reading right. Maybe it might have a fudge factor in there for fun. A concentration of 0.001 has a pH of 3. Okay. So you notice that as we take a look at these, these concentrations are directly related to those pHs. But if we go back to our weak acid again, take a look at the weak acid, now not changing this concentration, right? The concentration stays the same, but for a weaker acid, the pH would be higher. For a stronger acid, the pH would be lower. So what that means is we can actually use less acid to generate a lower pH for our strong acids, all right? Or what we're saying here is if I put a mole's worth of strong acid into solution or a mole's worth of weak acid into solution, the weak acid might drop my pH by a few points. The strong acid is going to drop it by a way more, okay? Which means it's stronger. It can do more, that kind of stuff. All right? The stronger the acid, well, the more corrosive it is because the corrosive nature of acids comes from those hydrogen ions or those hydroxide ions. So again, the stronger it is, the more ions in solution, the more corrosive it becomes, okay? The stronger it is, the faster it reacts, okay? This goes back to our conversation on how concentration relates to the speed of a reaction. Well, more hydrogen ions, more concentration means faster reaction times, okay? So you have a higher concentration again, so it's going to react faster, okay? The more energy change we're going to see when it reacts, okay? Again, more ions are present, it's reacting faster, we're going to see a greater energy change. So everything gets more aggressive with stronger acids and strong bases, okay? They're the ones that are the most dangerous to us in terms of like corrosiveness or toxicity to people and organic tissue because of how corrosive they are, how fast they react, how big the energy change is, okay? Now, they're also better at neutralizing. We haven't talked about neutralizing yet, but neutralizing is the counteraction of a base to an acid. So an acid can actually neutralize a base. Now, one thing to note, they're not safer, okay? They're better at it, but not safer. And the reason why is because we have way more heat generated in that neutralization process because it happens faster, there's more energy change there. So even though the process is better, meaning it results quicker and easier, it also generates lots of heat energy. So that can be actually pretty dangerous for us, okay? And then last and most important, it's way more dangerous for us to handle, okay? So if you're working for a company and you're trying to decide on the chemicals you want to use, and you have strong acids versus weak acids, and their relative strength will play a role in what kind of personal protective equipment that your employees will have to be wearing, okay? I got a buddy who does this out in California, and he's walked into companies and said, well, you're using this acid, you're using this strength of acid, your employees have to have face masks, gloves, full suits, that kind of stuff. But then he'll say, but if you switch to this acid, it can still accomplish the same thing you wanted to chemically, and now all they need to wear is safety goggles and gloves. So it also creates a safer work environment. So part of his job is actually to take a look at these kind of things and say, hey, here's a way that you can accomplish what you still want, and it's better for your employees, it's safer for them and actually more comfortable for them. So that knowledge is something that he actually uses in his job every day as an environmental consultant out in California. Kind of cool. All right. All right. Now, we're going to end the video here because the next thing happens is we're going to talk more about that neutralization thing. Thank you.